Continuing on with thermodynamics, today we're going to focus on what is called the kinetic theory of gases. Now, I want to go ahead and tell you now, the kinetic theory is often just called that, the kinetic theory. I've also seen it called the kinetic theory of matter. I've seen it the theory of matter. There's a bunch of different names. The kinetic theory of gases is what we're going to universally call it in this class. Now, just as a reminder, last time we talked, we were looking at the introduction to thermodynamics, so this heat-driven motion, and we looked at a bunch of different concepts that were understood experimentally in the 1800s from a macroscopic perspective. Specifically, they looked at things like temperature, thermal energy, heat, the first and second law of thermodynamics, pressure, and they were able to notice trends connecting these and able to predict how certain things behaved in a macroscopic way. But there was no explanation for why anything did what it did. In physics, we very much care about the why. And so eventually, in the late 1700s, early 1800s, a model was created where basically a bunch of scientists and mathematicians said, well, you know, we can explain a lot of this if we just pretend that things like gases are actually composed of little microscopic particles. And if we pretend that that's the case, we can make all the math work out. So let's just do that. And this is the basis of the kinetic theory. So the kinetic theory of gases is a theoretical model of gases to explain why gases behave according to the fundamentals and laws of thermodynamics that we already discussed. Now, this kinetic theory was based on 4 key assumptions that we do need to know. So first off, assumption number 1, we say that gases are going to be composed of tiny particles called molecules or atoms, but specifically molecules, that have lots of empty space between them. Now, what that means is that these tiny particles are so small that there is way more space between them than just a diameter of a particle. They're very spread out. Additionally, they're so tiny and they're moving so quickly that we can largely ignore the effects of gravity, which makes our lives a little easier. The second assumption is that these particles are solid objects that obey Newton's laws. So that means that they're going to always travel in a straight line at constant velocity. They have inertia, unless they're acted upon by a force. And those can be forces from other particles or from the walls of the container. And when they do collide, they can apply forces to those things. The third assumption is that these particles are hard spheres that collide elastically. Now, by hard spheres, we mean we can kind of just treat them like little billiard balls. These particles, these molecules, we're going to see as little billiard balls, and they don't get deformed by anything. And remember, when we say collide elastically, what does that mean? That means no energy is lost. So when they collide, either with themselves or with the walls of the container, no energy is lost. That's very important. And lastly, we say that all of the gases we're going to be looking at are ideal. Now, what that means is, okay, if you learned about ideal gases or noble gases in chemistry, remember, they don't really react a whole lot. They kind of just exist on their own. So we're going to say all the gases we're dealing with, there are no electric forces between the particles, or there are no intermolecular, like basically one molecule and another molecule do not in any way interact unless they are colliding. Additionally, we're pretending like they have no interior structure. So that means no protons, neutrons, we're just treating them like one little billiard ball. As a brief note, when it comes to the kinetic theory, a big debate in the 1800s was, this is a theoretical model, so is this in any way like reality at all? And that was very, very contentious at the time. Some scientists said, yes, gases are really made of these tiny little billiard-like particles, and they really do behave in this way. And other scientists said, no, this is just a mathematical trick that allows us to analyze gases statistically and mathematically in a nice, simple, easy way. Nowadays, we know that this model is largely accurate because we know molecules and atoms are real things, which they did not know at this time, but simplified. You know, if we look at those assumptions, not all gases are ideal. The particles have interior structures with nuclei. The atoms can be deformed in a way. Additionally, they definitely lose some energy in some respects. So there's a lot of simplifications here, which makes it much easier to analyze, but the whole picture is pretty accurate. Okay, so to visualize what we've kind of been talking about now, pretend we have a box, and this box is sealed away from the environment, and in the box, we put some gas. So just some sort of gas cloud in here. This is how it would have been visualized at the time. But then when we start looking at the kinetic theory, we say, well, this gas is not just a big blob of stuff. It is actually a bunch of little particles all moving around at a ton of different speeds. They're moving specifically at a variety of speeds. They're not all going at the same speed. Some are going faster, some are going slower. They're going in random directions. And if we think about this, so what's the type of energy that anything can have? So we've talked about things like kinetic energy, internal energy, potential energy. That's really all we've really focused on. But if these, one, remember we said they're ideal, so they don't interact in any way besides hitting each other. So that kind of removes all potential energy, especially when we say that they're really not affected that much by gravity. So no potential energy. And you might say, well, they obviously have thermal energy. Well, the gas has thermal energy, but we just say the particles have kinetic energy. The gas as a whole has thermal or internal energy, but the particles only can possess, and this is key, can only possess kinetic energy. The only type of energy they have is from movement. Now, let's say we were to look at that box, and we were to count the number of particles that all had different speeds, and we were to plot it. Well, what would the shape of that graph look like? And you'd probably think, okay, well, it would make sense. There would be some sort of bell curve, that we would have basically the most probable speed, or the most common speed, would be some middle value, and we would have a normal distribution, which is also called a Gaussian distribution, where basically it just slopes off on both sides. So we have some moving faster, some moving slower, but the vast majority are right there in the middle. Well, that's not 100% accurate, actually. When it was studied, they determined that this was not accurate. Instead, the graph looks more like this. Now, I'm going to get rid of this gray one so you can see this a little better, but I just want you to know specifically the whole graph is skewed towards the slower end. All right? So let's talk about what this is. First off, we call this a Maxwell-Boltzmann distribution. Maxwell and Boltzmann both being physicists and statisticians. They studied statistics. And to basically model this, so it's called a Maxwell-Boltzmann distribution. So we get a large, sharp peak, and then as you see, it kind of trails off with this tail. The whole thing is kind of like shifted. And so now, the most probable or common speed, like if I was to pick one out at random, it would be a little below the average speed, because that is the most probable, but we have particles going much, much faster, so the average is a little bit beyond that. Now, this is specifically any sort of thing like this, either this Gaussian one or this Maxwell-Boltzmann one, are probability distributions. And what do we mean by, I'll admit I kind of messed up my drawing there. Should go a little bit more like that. There we go. What do we mean by a probability distribution? Well, what we're talking about is, okay, so let's actually get rid of that for a second. Good enough. So let's say you were counting, like physically counting, okay, I have, so many particles at this speed, and I have so many particles at this speed, and this speed, and this speed. And you could plot little bar graphs. So I could say, well, there were this many at this speed, this many at this speed, this many at that speed, etc. So this is basically just showing you counts of particles at every speed. Well, if that's the case, that means this whole shape here, if I was to add up all of these counts, well, that would just be the total number of particles, right? Like all these graphs here would be the total number of particles. So if I want to know how many are moving at a certain, if I want to know the percentage or the probability of some moving at a certain speed, I could say, well, for instance, at this speed here, I could say, well, I have this many, and then I could divide that by the total number, right? So if I want to know the probability, you could say the velocity, number at some speed divided by the total number. And that will give you some percentage, and that's the probability that you would select that if you were to select one particle from this gas. But the important thing I want to get here, though, is that this area here is the total number of particles. Okay? Well, why does that matter? Well, let's look at that. Okay, so I'm going to bring up another Maxwell-Boltzmann distribution, and you can see it goes up and it's a little bit skewed. It's not real severe, but it's a little bit skewed so that it's sloping down more this way. And this would be a relatively low speed average, we'll say. So like, for instance, this is all the particles, and we can see that the most probable one is this one here. So it's a fairly low speed average. Well, let's say we had these particles in a box, and let's say that the particles as a whole, the average went up. So on a whole, the particles moved faster. Now, we need to be careful. Just because the average goes up, we still have some particles moving extremely slow, and we have some particles moving extremely fast. Because when they hit each other, they are transferring speed to each other. So we still have some slow ones, some fast ones, and the peak will still be in the middle. But remember, we said that this whole area was the total number of particles. Well, if that's the case, that means if I'm to move to a higher speed average, this is going to start flattening out a little bit. Because this area, the total number of particles didn't change. So this area under the yellow curve, which is the total number, must be equal to this blue area under the curve. So even though my average has gone up, my area under the curve stays the same. And that is really crucial, that the area under the curve is constant, because we are not changing the number of particles. We're just changing the overall speed of them. And because we are spreading it out more, the curve has to flatten out for that area to be constant. And if I move it to an even higher speed, it's going to flatten out even more. So that now, this is my average. It's moved higher, but you notice it is flattened out even more. And these are still Maxwell-Boltzmann distributions. They still have that curve shape. Now, we're going to talk about this a little bit more in class, but I want you to think about something in general. What do we know that is correlated to speed? Well, we already said that these particles can only have one type of energy, specifically kinetic energy. So this is telling me that the low speed average means that these particles as a whole initially have low kinetic energy. As we speed them up, they get medium kinetic energy, and as we speed them up more, they get high kinetic energy. And we're going to find out and discuss this more in class, but kinetic energy is directly tied to another concept we've already discussed, which is temperature. So if we have a colder gas, the particles are moving at a lower speed, and we're going to shape like this. If we start to raise the temperature, the curve is going to go more to here. If we raise temperature to something hot, it's going to go even more flat and more spread out. Now that we've kind of formally defined what the kinetic theory is, we're going to go back to what we talked about last video and really redefine 4 key concepts in terms of now what we know is the true cause or the true meaning. So first off, we have temperature. And we already learned that temperature, this is notes you already took, capital T, and it is a macroscopic measurement of the relative hotness of an object or system at some moment in time. It is also a macroscopic measure of the average kinetic energy of a system of particles. Once again, This is macroscopic. Temperature is a macroscopic effect because we have to have many different particles to have an average kinetic energy. If you only have one particle, average doesn't really make a whole lot of sense. So temperature is a macroscopic effect that can be explained through a microscopic cause. And the microscopic cause is that these particles are moving around, they have different kinetic energies, and the average kinetic energy of the system correlates to temperature. Slower, lower temperature; faster, higher temperature. This is also why we will only be using the Kelvin scale throughout this unit. So if you have a temperature in Celsius, you need to convert it to Kelvin pretty much immediately. And why is that? Well, remember, the Kelvin scale does not have any negative numbers. And if you remember the equation for kinetic energy, which I'll go ahead and just write here, 1/2 mv squared, this is always positive. Velocity, if it's positive or negative, it's squared, always positive. Kinetic energy can only be positive, so it makes sense we would use Kelvin because there are no negative numbers. We only have then positive temperatures. So now let's discuss pressure. Remember, pressure is a macroscopic measurement of force distribution over a surface. So let's go ahead and go back to the box. And we have some container here with a bunch of gas particles moving around inside of it. Well, how do we think about pressure now in terms of the kinetic theory? Well, keep in mind, when any of these particles hit the wall and come back, they have undergone a change in momentum, right? Because that's automatically going to happen. They're changing direction. They're not losing speed because these collisions are elastic when they hit the wall, but they are changing direction. So there is definitely a change in momentum. Remember, this is lowercase p, this is capital P. Be careful. Well, what is another word for change in momentum? Hopefully you remember. Impulse. And the equation for impulse is F delta T. So that means that the walls of the container have to be applying a force to the particles so that they change their momentum. But we know from Newton's third law, so if the container is applying a force to the particles have to be applying a force back. This is the source of pressure. The source of pressure is a macroscopic, or what it is a macroscopic measurement of how there are trillions of gas particles and they are continually striking the inner surface of the container. And when they do that, those forces divided by the total surface area of the interior of the container, that is pressure. Lastly, let's return to this scenario. Remember, we have two boxes. One that's at a high temperature, so that means the particles inside of it, we'll say there's a gas stuck in this container, are moving really fast. We have another box that's at a low temperature, so the particles are moving much more slowly. Let's go and say, as soon as the timer starts, we basically open this up so that particles can travel between the two now. So if we do that, well, what is going to happen is we're going to start having particles going both directions, right? But overall, something we need to remember is that we have over here a certain amount of average kinetic energy from the temperature, here a much lower average kinetic energy, and now there is going to be a change in the average kinetic energy or the temperature of both boxes. And this is essentially what's going to happen. We're going to start having some faster particles move over here, some slower ones move over here. They're going to start striking each other. The faster ones are going to slow down. The slower ones are going to speed up. So we start approaching a new average that was lower than this average, but higher than this one. So this is heat. Heat we've previously discussed as a net transfer of thermal energy. That is a macroscopic way of looking at it. But a microscopic way of looking at it is saying that there's a net transfer of kinetic energy between two systems of particles. And eventually we're going to get to a point where the average kinetic energy of both is basically the same, which means we are at the same temperature, which we know also as thermal equilibrium. That the transfer of thermal energy is the same and it's balanced, so we have the same temperature, but that also means the transfer of kinetic energy is balanced and that they have, therefore have each box now has the same average kinetic energy or same temperature. So finally, what are our big takeaways for the kinetic theory of gases? One, we want to explain its purpose and the assumptions that are made by it. We want to make sure we remember those. You need to be able to identify a Maxwell-Boltzmann curve and distinguish between different curves based on the average speed, or therefore based on the temperature. And remember that the area underneath each curve is always 1, or the number of particles. And lastly, we want to redefine and reconceptualize all these different things we learned from the last video, such as temperature, pressure, heat, and thermal equilibrium. But now, instead of just looking at them macroscopically, we also want to understand what they really mean on a microscopic level. There are macroscopic effects, we notice them, but they have microscopic causes.